Yeah, thank you for having me, and thank you everybody for coming. Even though I can't see you, good evening, good afternoon, good morning, I guess. Yeah, I'm based at the University of Edinburgh. I'm a research fellow. Um, I'm going to talk about a sort of ice sheet wide look at plume upwelling and glacier-fjord geometry in my talk. And before I start, I'd like to thank the people who also contributed to this work. It just came out as a paper today. And so thank you to these co-authors, especially Dustin, Hilda, and Mark, who were fun to work with. So I'm really interested in the interaction between the Greenland ice sheet and the North Atlantic Ocean. And that occurs through long, deep, and narrow fjords around the margin of the ice sheet. So by long, deep, and narrow, I mean these fjords are typically tens of kilometers, maybe 100 kilometers long. They can be 5 to 10 kilometers wide, and topographically really spectacular with mountains, and the fjords are several hundred meters deep. And if you zoom in even further, you get to the calving front of these glaciers, which is, typically a vertical wall of ice, maybe 5 kilometers wide, again, several hundred meters deep. And at this wall of ice, lots of really fascinating heat and freshwater exchange occurs. And that seems to be really central to a lot of big questions that lots of people are thinking about at the moment. So we can think of fjords as being kind of conduits for two things, potentially. One is that they transport ocean heat up to the front of glaciers, where it can melt the front of the glacier and lead to dynamic responses. But in the other direction, any fresh water that's going to go from the ice sheet into the ocean also has to pass through these fjords. So they're kind of like a bottleneck in this ice-ocean system, where everything has to go through them. And sort of by way of introducing myself, the really big question, or one of the really big questions that I'm interested in, is, will ice loss from Greenland affect ocean circulation? And that sounds really grand to me, but what I really work on is trying to understand and characterize how fresh water gets out of fjords. And then on the heat side of things, I'm interested in how much Greenland will contribute to sea level over the next century. And again, that's a very big question. So really what I mean is I want to understand how ocean heat gets up fjords, how it drives melting, calving, and potentially glacier retreat. So it's sort of in this wider context that my talk sits today. I guess the other sort of context we could give this is what's happened over the past few decades. So there's been a real period of change in the Greenland ice-ocean system. And you can think of that in very many ways. One way is to look at terminus position change of tidewater glaciers. And in this decade, 2000 to 2010, and also since then, the vast majority of glaciers around the ice sheet have retreated. And understanding that and those dynamics is an active area of research, but no doubt it's due to some combination of atmospheric and ocean warming. And with that, we have seen Greenland contribute to sea level, to go from being in sort of rough balance in the 70s and 80s to now contributing rapidly to sea level. 15 millimeters since, say, 1980, according to this new data set. And if you were to slightly cheekily flip this plot on its head, that means that there's more fresh water going into the ocean than there was before. Okay. So one of the really big sort of important processes in the Greenland ice-ocean system are plumes. So plumes are concentrated regions of upwelling adjacent to tidewater glaciers. So they happen at the calving front. and they're driven by the release of fresh meltwater from beneath the grounding line of the glacier. And this fresh meltwater ultimately comes from surface melting of the ice sheet. So as the ice sheet surface melts, the water, because the surface of the ice sheet has moulins and crevasses, the water tends to find its way to the bed of the ice sheet, and then it flows out from beneath the grounding line and into the ocean. And because the water that's coming out is fresh water and the ocean is salty, the fresh water is much lighter and it's really buoyant, and it rises kind of like smoke coming out of a chimney, for example. And you see the surface expression of such a plume in this picture on the right-hand side. But really, plumes are ubiquitous around Greenland during the summer. So before I come on to that, this is just a sort of computer or a simulation visualization of a plume. So this would be like you were in the ocean in front of this glacier, looking back towards it. So you're looking sort of at a wall of ice in front of you, and at the bottom of that wall of ice, there's a channel delivering fresh subglacial discharge into the ocean, and it rises turbulently and mixes very vigorously with the surrounding water. So plumes are kind of ubiquitous around the ice sheet during the summer. So this is a plume at Helheim Glacier in southeast Greenland. It doesn't appear so often at Helheim because Helheim has this really thick ice melange, which may play a role in sort of suppressing the plume from appearing at the fjord surface. But it was on this occasion. And here are three other examples from Boding Glacier in northwest Greenland. These areas of open water in front of the glacier are the surface expressions of plumes. This is Kangerlussuaq upsermia in west Greenland. And this is Sakhalli upsermia a little bit further south, also in west Greenland. So what you're seeing in all of these cases is the surface expression of the plumes. You're not seeing, the whole plume, which is under the water. So why are plumes important? Well, I can think of three sort of principal ways. So I'll go through them in turn. The first is that they're a real key driver of fjord circulation, freshwater mixing, and export. So as a plume rises adjacent to the glacier, it pulls in surrounding fjord water, and that sets up a circulation that draws water towards the glacier at depth. And then the product of the plume is a new water mass called glacially modified water, which is then sort of exported back out down the fjord, and that contains this fresh water. And plumes are a really sort of big driver of this process. Plumes are also important in upwelling of nutrients. There's been a whole host of work on this recently, and the idea is that often the deep waters around Greenland are rich in nutrients, and if you can pull those up into the photic zone, where light can access the waters, then they can drive enhanced productivity. But whether or not they can actually do that is sort of explored by this figure, and the take home would be that it depends on the dynamics of the plume, where it gets to in the water column, and what the geometry of the glacier fjord system is. And then lastly, but not least, because this is the International Glaciological Society, not the International Nutrient Society or something, plumes also, of course, are very important for the ice sheet in that we think they are drivers of hotspots of submarine melting, and that they might be able to sort of eat their way back into a glacier and result in these kind of calving embayments like you see here. So with all of this in mind, the point of this talk is to set out to map plume upwelling and glacier fjord geometry around the Greenland ice sheet. So I'm going to first introduce the model and then talk about the data sources. So this all requires a model for the dynamics of plumes, and there is one which is sort of very standard now and has been used across lots and lots and lots of studies, and it's based on buoyant plume theory. And I've put the equations here for, I guess, those that are interested, but I don't mean to explore them too much. Maybe just looking at, say, the top four. These are conservation equations for mass, momentum, heat, and salt as the plume rises. And the point is that the, let's say, the mass or the volume flux of the plume can change according to the entrainment of ambient fjord waters and also due to submarine melting of the calving front. Its momentum changes due to the buoyancy of the plume and also due to a drag on the ice. And its heat and its salt change due to the entrainment of ambient waters, and again also due to submarine melting of the calving front. Although I would say that for this application, because I'm looking at plumes that have a lot of subglacial discharge, the feedback of submarine melting on the plume dynamics is not very strong. So many of these terms turn out to be quite small, as does the drag term. But the point is that you can model the dynamics of a plume quite simply with these equations. To give you an idea of what the solutions look like and an idea for plume dynamics, this is one solution of those equations. So if we look at the left-hand plot, you've got the volume flux in the plume. So it starts out about 500 meters below the ocean surface at the grounding line of the glacier. And its initial volume flux is just the subglacial discharge that's driving the plume. But because it mixes very quickly and pulls in that surrounding water, the volume flux increases rapidly as it rises. If you come over to the right-hand plot, the black line shows this is salinity. The black line shows the fjord salinity as a function of depth, and it's salty at the bottom and fresher at the top. Whereas the blue line shows the in-plume salinity as a function of height. So the plume initially starts as pure freshwater because it's subglacial discharge. It mixes very rapidly with the surrounding fjord water, so its salinity increases very quickly. And as it rises, there usually comes a point where the salinity of the plume exceeds the salinity of the ambient fjord waters. And that's an interesting point because the salinity really determines the buoyancy of the plume. So if the salinity of the plume is higher than the salinity of the fjord at the same depth, then the plume is no longer buoyant. It's no longer positively buoyant, it's negatively buoyant. So it wants to sink. So as the plume goes past this point, it starts to slow down. It does carry on though, because it has this momentum. And at some point, its velocity goes to 0, and that's as high up in the water column as it gets. And these two depths, which are shown in these horizontal lines, the plume neutral buoyancy depth and the plume maximum height, will come up again in this talk. Maybe a nice way of illustrating that is this paper from Dustin Carroll that had these MIT GCM simulations of a plume. And you can see these same heights on these plots. So if we look at the middle one, for example, the plume here is rising. It shoots up. At some point, it hits its maximum height where it stops rising. It comes back down and it settles around its neutral buoyancy level. Okay, I think I will possibly skip these. I'll do one of these slides. So what happens if we were to change the subglacial discharge, for example, if we double the subglacial discharge, so this is now the redder lines, then the plume volume flux is twice as large at the base, and then it increases more rapidly than it did in the lower subglacial discharge case. If we again go to the plume salinity, you'll find that the neutral buoyancy level is a little bit higher up in the water column, and the plume reaches further up in the water column. So because the velocity goes to 0 higher up. So this is kind of what you would expect if you pump more water into the bottom of the fjord. You get a more vigorous plume that rises further up before it stops. Okay, so I'm going to explore those dynamics around the ice sheet. To do that, I need a data set for glaciers and fjords. So for glaciers, we started from a list of 243 fast-moving glaciers, but we removed glaciers that have shallow grounding lines or small subglacial discharge. And that's because if they're shallow or they've got small subglacial discharge, they won't be big contributors to upwelling. We also removed glaciers that have a deepest path to the ocean that's shallower than 25 meters. That was largely to remove some fjords where we didn't really believe the bathymetry. So that left overall 136 glaciers in this data set. And you can see them in the purple around the ice sheet here. We also wanted a fjords data set because we wanted some key statistics about the fjords. But this is harder because it's not really clear how to define a fjord. So, on the left, we've got Ilulissat Ice Fjord, where Jakobshavn drains into. And in this case, I think it's fairly straightforward. You would say that, this part is the fjord and the fjord mouth is here, and everything outside of that is something that's not fjord. But on the right-hand side, at a larger scale, this is in East Greenland, and this is Scoresby Sund, and then you've got a really deep fjord which goes up to Daugard Jensen Glacier. In this case, where would you say the mouth of the fjord is? Like, do you draw the mouth of the fjord away out here, or I don't know, do you draw it here? So it's kind of an ambiguous question. When is a fjord not a fjord? But we wanted a consistent definition. So what we did was to try basically drawing a boundary around Greenland, including all mainland ice and land inside the boundary. And then you kind of shrink wrap Greenland, basically, such that everything outside of the boundary is, I don't know, continental shelf or ocean, and any ocean which is left inside of that boundary is defined as a fjord. There is a MATLAB function which will do this for you, and it has a parameter which is you can think of as a shrink factor. And if you set that equal to 1, then you get the tightest possible wrap where you effectively have the shoreline and grounding lines. And in that case, you would have no fjords. And if you set alpha equal to 0, you would have a kind of looser fit, and the fjords would be quite generous. We use something in the middle, which is alpha equals 0.5. So to show what that results in then, it means, so the black dashed line that you see on this plot is this boundary. It means that, you get the expected definition of a fjord for Ilulissat Ice Fjord. But it's also plotted in blue on this left-hand side. And it means that Scoresby Sund, the outer part of it, is not defined as a fjord. That's defined as ocean. But the narrow fjord that goes up to Daugard Jensen would be a fjord. I guess there's a risk that this all seems a bit abstract. I guess the point is that depending on the application, you kind of want to try and separate fjords from what's outside. A practical way to do that might be if you're trying to force an ocean model with freshwater from the ice sheet, maybe you would take a fjord to be anything that was not represented by the ocean model. So maybe the ocean model has sufficient resolution to represent the inside of Scoresby Sund, but it doesn't have enough resolution to get the narrower fjords inside of that. Okay, we also needed some inputs for the plume model. 2 inputs. One is subglacial discharge flux, and one is fjord stratification. So the discharge flux, there's now a sort of off-the-shelf product available produced by Ken Mankov. It basically takes regional climate models and then does some flow routing to define hydrological catchments for each of the glaciers. And for the plume simulations, we used the mean summer value, so June, July, August, during 2010 to 2020. And we also needed fjord stratification. These come from CTD profiles in the fjords. Much of the ones used in this study come from oceans melting Greenland, but there's some sort of other additions from Sermelik, from Gotabsfjord, from Sakardalek Fjord. The cool thing is that we're now at a point where we have quite good coverage, at least of snapshot CTD profiles around the ice sheet. So that if you look at the distance from a CTD cast to, from a glacier to its nearest CTD cast, of the 136 glaciers, the vast majority of them have a CTD cast within 30 kilometers. And that means it's a CTD cast from within their fjord. So that's really quite something, I think. And this is an excuse to show a nice picture to say that collecting CTD casts is, on the one hand, quite hard work, and on the other hand, really good fun. But yeah, I appreciate all the CTD casts which we've managed to use in this study. The results are going to be couched in terms of 6 key quantities. 2 of them you've been introduced to already. It's the maximum height reached by the plume, and the other one is the neutral buoyancy depth of the plume. So another one is the grounding line depth. That's the depth of the bottom of the glacier at the calving front. That's where the plume starts out. And then there's 2 fluxes which we're going to look at. One is the subglacial discharge flux. That's what comes out from beneath the glacier and initiates the plume. And the other is the plume upwelling flux. That's defined as the flux carried by the plume at its neutral buoyancy depth. So it's basically a measure of how much upwelling the plume is doing. Let's see, why might you care about these? So the plume maximum height you might care about, and the plume maximum height you might care about because that's the maximum height reached by the plume. And from a nutrients perspective, you're interested in whether that's in the photic zone. The plume neutral buoyancy depth is really setting the depth. It's a sort of fundamental depth of the circulation in the fjord, and it plays a role in setting the depth at which fresh water is exported out of the fjord. The plume upwelling flux tells you sort of how quickly this circulation is moving and how much might be exported to the fjord, to the ocean. And then there's the 6th key quantity that I haven't mentioned so far is the fjord effective depth. So that's the deepest depth at which the glacier is connected openly to the ocean. So if there's a sill, a shallow sill, then the fjord effective depth would be that sill depth. But if there's not a sill, then the fjord effective depth might just be, the depth of the fjord. Okay, so 27 minutes past 9, we're onto the results. So here are tidewater glaciers, 136 of them in this data set. They're ordered by grounding line depth. So the blue is the grounding line depth of these glaciers. The red is the fjord effective depth. So that's the depth at which it's sort of openly connected to the continental shelf. The purple is the plume neutral buoyancy depth. And then the yellow is the plume maximum height. So grounding line depths vary from about 1,000 meters up to about 50 meters, which is where we cut off the data set. For those grounding line depths, the fjord effective depth is very variable. So there's a lot of variability in, for example, sill depth as you go from fjord to fjord. But in most cases, the fjord effective depth is shallower than the grounding line depth. So either there is a sill or the continental shelf is shallower than most of the fjord. And then neutral buoyancy depth sits in the sort of 200 to close to the surface kind of range. And you might notice that it decreases or it gets shallower as the grounding lines shallow out. So there is a relationship there where the shallower the grounding line, the further up in the water column the plume gets. And then lastly, the plume maximum height is the shallowest of all. And for a lot of these systems, the model is suggesting that the plume does get to the surface, and that's where you would see that kind of brown patch of open water at the fjord surface. You can also look at it in a histogram if you wanted. So the grounding line depths scatter out like this in terms of a histogram. Then the next up is the fjord effective depth, the plume neutral buoyancy depth, and then the plume maximum height. So now I'll come on to the fluxes. So again, on the x-axis, we've just got 136 glaciers plotted from left to right. And the blue is the subglacial discharge. And the units here are a bit oriented towards oceanographers. So they're in terms of millisverdrups. So a sverdrup is 1,000,000 meters cubed per second of water. So a millisverdrup is 1,000 meters cubed per second of water. So the largest subglacial discharge fluxes are around about 1,000 meters cubed per second. Yeah, so that's the flux initiating the plume. However, the flux, once the plume has got to its neutral buoyancy level, so it's entrained all of this water, is about 2 orders of magnitude higher. So the highest upwelling flux is getting on for 50 or 60,000 meters cubed per second. So in other words, this fresh water really does an awful lot, drives an awful lot of upwelling. I think this is maybe my favorite plot of this work. So it's effectively like a histogram, and then you fit a probability distribution to it. So it's basically a probability distribution function. What it's showing you, the left panel, is subglacial discharge and what depth it comes in at. So it's basically the subglacial discharge fluxes plotted against the grounding line depth at which those fluxes are coming into the ocean. And the integral under the curve here is the total subglacial discharge, which is 0.02 sverdrups. So that's 20,000 meters cubed per second. And subglacial discharge is relatively spread over all these depths, but there is a bit of a concentration of it around 300 to 600 meters or so. However, once it's done being upwelled, that subglacial discharge all sits very much in the upper water column, and the fresh water is very, very diluted. So the flux, once it's all upwelled, is over a sverdrup, so over 1,000,000 meters cubed per second, and it all sits in this upper water column. So all told, what this plot is showing is that although the fresh water is delivered into fjords, at a certain depth, the upwelling by plumes basically concentrates all of that fresh water into the upper water column. So this 1 sverdrup value, basically that's 1,000,000 meters cubed per second on average in summer is upwelling around the ice sheet. How certain can you be about the value of that number? Well, here's some things that change it. So its default value is about 1 Sverdrup. If you look at the lowest discharge month between 2010 and 2020 during the summer, it's about half a Sverdrup. If you look at the highest discharge month, it's about 1.5 Sverdrups. If you were to spread the discharge out a bit more when it comes out from beneath the glacier, it's about 1.5 Sverdrups. If you were to concentrate it, it's a bit less. And equally, there's an entrainment coefficient in the plume model, which determines how much entrainment happens into the plume. And you can see how much that changes the upwelling. So this total upwelling of about a Sverdrup, isn't a particularly precise number, but maybe something between 0.5 and 1.5 Sverdrups is a fair estimate on how much total upwelling happens. The last point on the fluxes is to look at renewal time. So if you know how much water is being entrained by the plume, and you have an estimate of the volume of the fjord, which we have because of the definition of fjords that we made, then you can calculate a simple time scale, which is the fjord volume divided by the upwelling flux, which tells you sort of how long does it take the plume to entrain all of the water in the fjord, basically. And so that's plotted here for the 136 glaciers. And the dashed horizontal line shows you 100 days. And the reason to plot that is that these systems that sit below that suggest it's for those systems the plume is able to sort of turn over all of the waters in the fjord in less than a single summer. And that means that those fjords then are going to be more likely to react quite quickly to changes in the ocean happening outside of the fjord. For the sake of time, I'll skip sector by sector, but there is a plot in the paper where we look into how this might vary by sector of the ice sheet. So to sort of come to a sort of discussion of these results, I do want to emphasize that plumes are not the whole story. They're only part of the story. So there's many other drivers of fjord circulation and lots of other ways that mixing occurs in fjords. To sort of illustrate that, there has been observational work on how much fresh water is exported from fjords or how much mixing happens in fjords. One such paper was Baird 2018. They estimated that there was a glacially modified water export of 74 millisverdrups from Sermelik Fjord. In this work, our plume upwelling flux is in the region of 18 to 47 millisverdrups, so it's significantly less than they estimated. And the reason for that is these other mixing processes which are happening beyond the plume. So they're clearly important in further diluting fresh water and setting its properties before it is exported. Similarly, a recent paper by Morven Mulvik looked at Upernavik Fjord, which is further north in northwest Greenland, and they found that plume upwelling comprised about 60% of the glacially modified water in this fjord. So, there was an additional sort of 40% of mixing going on due to processes beyond the plume. And one such important process is a sort of horizontal recirculation of waters in fjords. So, I've been talking about vertical upwelling. Once the waters have done doing that, they can do some horizontal recirculation. And I wanted to sort of reference this paper by Ken Zhao, which I thought was really great at exploring these other mechanisms of mixing. Okay, so plumes are not the only story. There's some caveats to the results I've presented. One is that we don't really know how subglacial discharge comes out from beneath glaciers, so we don't know if it tends to be channelized or distributed, and that makes quite a big difference to the results. Plumes are more efficient at upwelling if the subglacial discharge enters the fjord in a distributed fashion. So if you make the sort of channel or the conduit wider that the subglacial discharge is coming out of, then you get a lot more upwelling. And you also get a lot more submarine melting. And that's very unknown at the moment. I think the other big caveat to what I've presented is that it uses snapshot profiles of, snapshot CTD profiles of what's happening in the fjords. And we know that fjords show a lot of variability in their properties. And that's been investigated by many authors, but one such paper was by Eva de Andres at Sakardalek Fjord. And they found that from one year to the next, a plume could get to the surface or not, depending on the fjord stratification. And that's not something we've managed to take into account because we were looking at the whole ice sheet. So there wasn't multiple CTD profiles available in lots of fjords. And the last part is that I, motivated this by saying that I'm interested in, or we're interested in, how freshwater gets from the ice sheet into the ocean. But actually this analysis has not covered the majority of the freshwater that comes out from the ice sheet. So if you look at the freshwater input to the ocean over the 2010 to 2020 time period, there's obviously liquid forms, meltwater, and solid forms, icebergs. Actually, the analysis I've presented, which is marine terminating glacier subglacial discharge, is only 13% of that flux. The rest of it is 7%, is also from marine terminating glaciers, but it's not included in our analysis because we didn't look at all glaciers. 28% of the flux is from land terminating glaciers, so that will enter the ocean from rivers at the fjord surface, which is very different dynamics to entering the ocean at depth. And then I guess the big one is solid ice discharge. So that's half of Greenland's freshwater input to the ocean. Although we can't tell the difference between solid ice discharge and submarine melting. So there could be some submarine melting. But regardless of that, I guess the point is that melting of icebergs in fjords is a really important process, and we want to understand how they melt and where that fresh water ends up in the water column too, if we're going to really characterize how fresh water gets from the ice sheet to the ocean. Almost lastly, I wanted to emphasize that all of the data sets and the code for this project are available. So it was published today. The data sets and the code are on Zenodo and GitHub. To highlight some of the supporting information for this paper, in the supporting information, there are maps of every fjord system that we delineated with key statistics about those fjord systems and the sort of key plume model outputs. And then all of that data is also available in a spreadsheet as well, if that data is useful to anybody. So I'll sum up there then. So this has been a sort of first ice sheet wide inventory of plume upwelling and fjord glacier geometry, covering 136 major glaciers, which accounts for the vast majority of the ice discharge from the ice sheet. One of the big take-homes is how efficient subglacial discharge is at driving upwelling and driving fjord circulation. So just 0.02 sverdrups, or 20,000 meters cubed per second of summer subglacial discharge from these glaciers produces about 1 million meters cubed per second of upwelling and upwelled water. And although the the input of the subglacial discharge is quite distributed over 0 to 1,000 meters below the ocean surface. Once it's undergone that upwelling process, all of that fresh water really sits in the upper water column at 0 to 300 meters depth. Because that upwelling process is so efficient, it also means that the fresh water is very, very diluted by the time it's undergone that process. And so when that water is then exported to the shelf, it is going to be in the subsurface, and it's going to be very, very diluted. And so that's an important feature for representing, for giving freshwater boundary conditions to ocean modelers, for example. If you take the fjord volumes and these fluxes, then a back of the envelope calculation suggests that plumes can renew most major fjords within a summer. So that means that over the course of that summer, the fjords will respond quickly to changes in ocean temperature outside of the fjord. We can look at the fjord effective depths. So that was the open path from the fjord to the shelf. And for 82 out of the 136 glaciers here, that path is deeper than 200 meters. And that means that deep warm waters will reach most major glaciers. So there's that open path between the ice sheet and the ocean. And lastly, we can also look at nutrient upwelling and where plumes reach in the water column relative to the photic zone. And there's a paragraph about that and some analysis in the paper, but I haven't really focused on it today. And I think I'll leave it there, and thank you very much for your attention.
Thank you very much, Donald. As usual, we'll take questions by getting people to just indicate in the chat that they have a question. And people on Facebook can also ask questions. We already have a comment on Facebook saying, thank you very much for a great talk. From Juliana Marini Marson, and saying, I'm currently looking into how to better represent iceberg melt plumes in a sea ice ocean iceberg model. Let's see how that goes. If anyone has any questions on Facebook, please pop them there. While we're letting people get to, oh, has this just arrived in the chat? Roger, do you want to unmute yourself and ask a question?
Yeah, sure. Thanks very much. I've finally learned to start typing questions into a Word document during the meeting rather than put incoherent ones in at the last moment. Thanks a lot, Donald. That was really fascinating. I just wondered earlier on in your talk how seasonal all these results and models might be, given what we know about how ocean water changes temperature during the year, or is all the input from the Atlantic below the, what's it called, the thermocline or pycnocline or whatever, and so at a stable temperature regardless?
That's a good question. I think the main seasonality in this sort of whole story is from the subglacial discharge, because that water that's coming out from beneath the grounding line is sourced from melting of the ice sheet surface, and that only occurs during the summer, really. So that supply is not from the surface melting in the outside of the summer. That supply is very much reduced during the winter. You still probably have a bit of water coming out because you have melting happening at the base of the ice sheet too, but it's very much reduced. In terms of the seasonality from the ocean, I think you're maybe right. I think in the really deep fjords, there is some seasonality in the deeper waters, but it's a little bit more muted. Maybe some of the shallower fjords would experience a lot more seasonality. But you also could have seasonality because fresh water can build up in the fjords over a season and then maybe be released over the course of a winter. So that would give you, a freshening of the fjord seasonally as well. That's a rambling answer, but I think that the dominant seasonality comes from the subglacial discharge. So, you get very much less upwelling during the winter or outside of the summer.
Sure. No worries. A rambling question as well. So thanks very much. Enjoyed that.
Yeah.
Are there any other questions for Donald? I was going to ask you how well we actually know the bathymetry of all these fjords. It's always struck me that it's rather poorly known. I wondered, how much of a problem that is.
That's great. I have a slide for that. I hope you can see this. This is bed machine version 4. It's showing the source of the bathymetry around the ice sheet. So there's yellow is the sort of ship measured bathymetry. The red is the gravity inversion. And then anything else is kind of interpolation, or I guess sort of really intelligent interpolation. So I guess the point is it's all a bit small to see, but actually there is ship measured bathymetry in really quite a lot of fjords now. So in a lot of cases, I don't think it's too bad, but there are still isolated cases where it doesn't seem right, as in it's looks like a really big fjord, but the water depth apparently is about 5 meters or something like that. So I think it is. Yeah, I think it is good enough to start to do this sort of study now, if you're careful. Yeah.
Thank you. So Roland, you've got a question. Do you want to unmute yourself?
Hi, thank you very much. Fantastic talk. Fantastic piece of work, Donald. I was interested in the discussion you had there towards the end in looking at uncertainties of the matter of plume widths versus the amount that's flowing in. Mm-hmm. You showed that increasing with plume widths, but presumably eventually you would have a plume that was so distributed that there really wasn't a vast amount of buoyancy forcing being described, and I'd expect that to detrain at a quite considerable depth. The earlier question that I was formulating as you were talking was the fact that a lot of this subglacial meltwater routing work provides opportunity to think of where there could be several plumes per glacier. Mm. And what you seem to be suggesting is that how that is distributed, whether 4 local plumes versus all that flux being put into one plume would be important. The other aspect is, looking back, I think your model doesn't seem to explicitly allow for the transverse, almost diffusive spread of the plume as it rises. Perhaps you could comment on those aspects. Thank you.
Yeah. I guess the last one, yeah, you're right. It doesn't allow for the transverse growth of the plume. I think that's okay as long as the plume is wide enough in the across glacier direction, because the entrainment that's happening at the growth that's happening at the sides is not, I guess, changing the cross section of the plume significantly compared to its growth away from the ice. But I think if you had a very narrow plume, then that would be a problem. On the sort of multiple plumes angle, I guess, like in theory, if you knew the bed topography and the ice thickness really well near the front of a glacier, then maybe your routing could be precise enough to start to, isolate multiple channels at glaciers. In fact, there was a paper by Mason Fried which did that and did manage to match up drainage pathways with observed plumes at the fjord surface. I guess in this study we didn't do that, partly because of the scale, so we kind of lumped everything together for each glacier. I guess I wonder whether at an ice sheet scale the data sets are good enough to at the front of the glacier to get the routing to work like that. One defense of what we've done is that because of the way the plume model works, a single plume of 500 meters width is actually identical to two plumes of 250 meters width. So implicitly, we've included the assumption that we've included the possibility that there would be multiple plumes. And then I think just your very first question was about whether there's some limit where if you keep spreading out the waters, eventually it becomes less efficient at upwelling because the buoyancy is so sort of spread out. I think you're right that you probably would get there in the end, depending on the fjord stratification, because how much you're upwelling depends on the buoyancy flux, but also on how far the plume rises. And if you really spread out the discharge such that it's a really weak source of buoyancy, then it won't rise very much, and so it won't entrain very much. So I guess eventually, yeah, you could spread it out enough that your entrainment flux would start to go down again, I think.
I could just say, I mean, you only showed us 3 data points, but it looked like a pretty continual upward increase in the total flux that was generated. Now, there has to be a law of diminishing returns somewhere in that. Otherwise, as you were just indicating at the end, you get the situation where a several kilometre wide input would seem to be going to have catastrophic effects, and that clearly can't be the case, because in that limit there's in fact no discernible buoyancy contrast. So I think you have to be careful about how your input flux is. I mean, there are 2 senses of flux here, one in terms of the 1D model and the other in terms of it's almost a question of what the initial velocity is, I suppose. Anyway, thank you very much.
Okay, yeah, no, those are good thoughts, thank you. Yeah.
Paco, I think you have a question as well.
Yes, thank you. Nice talk, Donald, and really clearly explained as usual. I'm curious about you have shown in a slide somehow the sensitivity of the fluxes after upwelling to the changes in various parameters, for instance, in the entrainment coefficient, but also to a doubling of the subglacial discharge. And my question here is whether this, so how well constrained are these parameters? I mean, when you say, for instance, that the change in this entrainment coefficient between 0.05 and 0.15, is this the usual range of the variation of the entrainment coefficient? Or if you know that, for instance, the subglacial discharge is a given value, is it normal from your experience that you can be missing the real quantity by half, or can be double, can be half?
I mean, on the entrainment coefficient, I think on the slide here, 0.05 to 0.15, my impression is that that's a fairly generous range. I think it does lie between those values. And that comes from kind of laboratory scale experiments, but also, I guess, a few studies that have done some plume modeling and compared to observations in fjords in Greenland recently. So I think that's fairly good. As far as the subglacial discharge goes, I think that's trickier. I wouldn't want to say how much it could be wrong by. I mean, one thing I will say is that Ken Mankov, who I did see on this call and whose data set I'm using, did do a lot of validation at land terminating margins where you can actually measure what's coming out of the glacier. And so at those land terminating margins, it does a reasonable job, is my overall impression. So that gives a bit of confidence for the tidewater glaciers, but it's very, very difficult to measure it because it's coming out so far beneath the ocean surface. I think you can do it from budgets using hydrographic profiles, but the uncertainties are quite large. Yeah, I see that. Unless you want to come back, Paco, I see that Ken has his hand up.
Yeah, I see. Thank you.
I
can't hear you, Ken, for some reason.
We hear static.
Can you hear me now?
Yes.
Okay, sorry about that. So a question or two questions. One relating to the issue of if everything's spread out, I guess they're both related. If everything's spread out and there's no initial buoyancy, the plumes won't go anywhere, that comment, which is we see a lot of plumes on the surface. And so we know that it's not coming out necessarily at this very thin line all over the place. But did you validate this, right? We have knowledge of where plumes are from Landsat imagery, where and when they show up. Mm-hmm. I didn't see any mention of that. Does where you say they should hit the surface match where you see them?
I haven't done that at the ice sheet scale. That would be nice to do. Yeah. Okay. We had some discussion for individual systems that I had some personal experience of, Circadlight Fjord, for example, or Sermelek and that sort of thing, but not at the ice sheet scale. That would be a fun thing to do.
Well, yeah, I mean, even a sparse check in a few fjords where the model says they do or don't hit the surface.
Yeah.
Okay, thank you.
Did you have a second question, Ken? You sort of indicated at the beginning of that you might have more than one, but...
Oh, no, it was the comment and just the related that the coming out under the entire glacier wouldn't create a plume is correct, but we see the plume. So we know they often come out in a concentrated area with enough initial buoyancy to hit the surface. And
Roger is asking a glacial geomorphological question that I haven't seen asked before. I don't know whether you want to unmute yourself, Roger.
No, just a tangential thought that's probably for another evening or day or morning, wherever you are. But if these toward glacier flows are consistent, maybe pause in the winter, it's the kind of thing that sedimentologists boast that they can see in varve deposits and so on. I just wondered if you'd picked up anything on that from conversations with geology colleagues. And I was also wondering about big forcing events like weather. What happens when weather pushes all your physics in a different way? But again, something for another night or day.
I'm very happy to leave the geomorphology for another night or day because I don't really know anything about it, I must say. On the weather pushing things a different way, I mean, like, one other big driver of fjord circulation that I didn't mention is intermediary driven circulation, where, for example, in southeast Greenland, you have big storms tracking along the coast that change the water masses on or change the density structure on the shelf, and that causes really rapid flushing events and exchange between the fjord and the shelf, and that is another big driver of fjord circulation, especially in the winter.
I think that we've come to the end of the questions there. So thank you very much indeed, Donald. That it was indeed a really clear and fascinating seminar this evening. I just should be telling people about the next seminar, which I think you can do for me. Thank you. So next week we have Jane Hart from the University of Southampton talking about exploration of the subglacial environment. So it'd be nice to see people next week. So thank you very much indeed, Donald, and thank you to the audience and for all the questions, and see you again.
Thank you.